name's Sydney. I'm the Outreach Director here at REAP, the Renewable Energy Alaska Project, and we're so excited to have you join us in our fourth installment of our fall speaker series, where we're going to be talking about tidal energy in Cook Inlet with Levi Kilcher and David Thomas, who I'll introduce a little bit later. I wanted to start out with a quick and important land acknowledgement. So I am zooming in here from Anchorage, where I'm from, on Dena'ina Elnena lands, and REAP staff live and work on Dena'ina Elnena lands Atnanen and Linget Annie. We acknowledge the thousands of years of stewardship of these lands and the indigenous knowledge and ways of life that continue to guide us today. So as you all are joining, we invite you to introduce yourself in the chat and share which lands you're on, calling in from today. And you can figure that out by going to nativeland.ca. I just shared the link in the chat, and it's also on the slide here. So yeah, we encourage you to introduce yourselves, share where you're calling from, and see who else is on the call today. It looks like we have a really great group. And I'm going to get us started off with some housekeeping items. So we have two presenters today, and we're going to leave a good chunk of time at the end for question and answers. So we might answer a few live as they come in, if it's really, really relevant to what's happening in that moment, but we'll save most of them for the end. And we encourage you to ask questions using the Q&A button that should be at the bottom of your screen if you're using Zoom on your computer, and you should also have a way to do this on Zoom if you're using a mobile device. So there's a Q&A button. It has two little chat symbols, and we really encourage you to do that so that we're actually able to sift through the questions, and the chat box can be more for discussion and comments. So please use the Q&A box. And also feel free to share resources and discussion and stuff like that in the chat. As I shared, as we just got started, this event is currently being recorded. It will be uploaded to REAP's YouTube channel, and we'll share the link to that tomorrow. Everybody who registered for this event will get that link emailed to them, and you can also just look us up on YouTube. So a little bit about REAP. We are a 501c3 nonprofit. We're based in Anchorage. We also have a hybrid Juneau office led by our energy catalyst and STEM educator, Clay, who's based out of Juneau. And we are a coalition of 70 dues-paying members, along with other partners and donors that support our work locally, regionally, nationally, and internationally. Our mission is to advance clean energy in Alaska. Clean energy means both energy efficiency and renewable energy. And you can go to our website, alaskarenewableenergy.org, to learn a lot more about the work that we do. We know at REAP there's 4 pillars for increasing clean energy. The first one is technology, which we honestly don't work directly in this realm. We aren't an engineering firm, but some of our members are, and some of our partner organizations do this work. The next pillar is funding. On the funding side, REAP has been pushing for a green bank in Alaska, which is a quasi-public bank that would fund clean energy projects. We also have a bill introduced by the governor in the last legislative session for this, to establish a green bank, and we're hoping it's passed this coming session. We, related to that, work in policy. We're right now working really hard to establish the first electric reliability organization, which would be on the rail belt electric grid. This work has been ongoing for quite some time, and we helped get some legislation passed a couple of years ago, and are now working hard on the implementation side of it on multiple levels. Our second speaker series was focused on this, so you can find the recording on our YouTube channel if you want to learn more. And finally, the fourth pillar for increasing renewable energy is people. This is where REAP does the bulk of our work. Almost half of our staff is working on K through 12 STEM education and teacher trainings. Some of those folks might be on the Zoom with us now, so if you are, please say hi. We also lead the Alaska Network for Energy Education and Employment, which works on workforce development, and we're part of the Sustainable Southeast Partnership, which is a community-led and oriented approach to advancing sustainability in Southeast Alaska. And finally, we'll jump into our presentations here. I'll do a brief introduction of our panelists. First, we're going to be hearing from David Thomas. He's the Director of Strategic Services at the Homer Electric Association. David will share the local utility perspective on tidal energy in Cook Inlet. And then we're going to hear from Levi Kilcher, who is a researcher with the National Renewable Energy Laboratory, who we also call NREL, and he leads their ocean energy resource assessment and site characterization activities. Levi is going to talk about some tidal energy resource measurements made over the summer. So as I shared earlier, we'll end our speaker series with a Q&A section. We should have about 15 minutes for this. So please use the Q&A button throughout the event to ask those questions, and we'll get to as many as we can, and we'll also follow up with you if there are a bunch remaining. And finally, before I pass it to David, I want to thank our sponsors for the event, SERI, Advanced Energy Economy, and Siemens sponsored this event and allow us to be able to put it on and bring in amazing speakers like David and Levi. So yeah, I'll pass it to David now, and thanks everybody again for joining us.
Hello, David Thomas, Director of Strategic Services at Homer Electric. One of my responsibilities in that role is to get us from where we are to our board of directors goal of being 50% renewable by 2025, which is a very ambitious goal. I believe the most ambitious on the rail belt. Not unachievable. You can look at Kodiak, who started much earlier and has gotten, I believe one of the things I say is 100% renewable 97% of the time. But let me go to my screen share and show you a few things about our system. So you see some facts and figures there about Homer Electric. And we currently generate 86% of our energy from natural gas. We burn most of that in our combined cycle plant in Nikiski on the Kenai Peninsula. And we spent a lot of money taking a simple cycle combustion turbine and using the waste heat from that turbine to generate steam and get about 40% more energy for no more natural gas consumption. So we write a smaller check to the gas company and a larger check to the bank for all of that capital equipment. But that was a significant step forward in our.
Hey, David, you're not sharing your slides quite yet.
Oh, thanks. Sorry. Let me. Oh, I apologize. There was one more button I needed to click. Okay, there you go. Some facts and figures about Homer Electric. As well as our service area here in purple. So 86% gas, as I was talking about, and then 14% hydro, about 10% of our energy from the Bradley Lake Hydro Project that came online in 1991. And then another 4% from Battle Creek water that was diverted behind the Bradley Dam to add more energy to that project. That came online in August 2020. So we've had part of one summer and all of another summer of additional water going behind the existing Bradley Lake facility. Looking on the right, you see these colored areas, which are the 4 cooperatives along the rail belt, plus down there in green, the municipal utility of Seward. These utilities in South Central have traditionally all been about 90% gas-fired and about 10% hydro. then with the recent addition of Fire Island Wind going to Chugach, and on our own system, we are additionally looking for new hydro options. Let me switch to my next slide. The Kenai Peninsula is resource rich in a number of ways. We have the Bradley Lake Hydro Facility, the largest hydro facility in the state, and depending on how you view it, perhaps the largest battery in the state. You can't charge it, but you can discharge it when you let the water run. We do have also the largest chemical battery in the state, 37 Tesla megapacks located at our generation facility in Soldotna. Part of the motivation of that battery was to incorporate more non-firm renewables, and part of it, in addition to making our combustion units operate more efficiently. That is being charged for the first time this week as we spend this month commissioning it. But the Kenai Peninsula also houses Chugach's Cooper Lake Hydro Facility, a little bit off this map to the right, out of Moose Pass. We've obtained a FERC permit for Grant Lake, which is almost a run-of-river hydro project up above Moose Pass. And the ridges and hilltops on the peninsula are known to be windy resources, and a few of them are near roads or transmission, which is what can make or break many renewable energy projects. You often hear bandied about. On this map on the right is the transmission system, and those gray areas are largely private property parcels, so give you some sense of the more settled areas of the peninsula. But if you're not on the existing transmission system, you hear rules of thumb of $1 million a mile to install new transmission, and somehow it always ends up being more in Alaska. And if you're not on the road system, you also hear estimates of $1 million a mile. But the road for Battle Creek was through some nasty terrain and ended up being about $8 million a mile. So simply seeing a hydro prospect or wind or solar prospect, often that is driven by where it is located. And of course, today we're talking about tidal, and Levi will later discuss how the tides are so excellent here in the East Forelands area, which is adjacent to the highway system and adjacent to our existing transmission lines. And where those things, the resource, the transmission, the road infrastructure comes together is where you can make a project happen that otherwise might not pencil out when 50 or $100 million evaporates into infrastructure. So location, location, location. Any renewable project often has a hurdle because renewable projects in terms of wind and solar, to a partial extent, tidal, are energy, they are not capacity. We have dials which we can turn up and down our hydro facilities. We have dials we can turn up and down on our gas facility. And we must, every month of the year, every minute of every day, generate exactly as much electricity as our members are using. Currently, or until this month, that was hydro and that was gas. Starting this month, it's also a big chemical battery system that allow us to meet those continuous needs. Wind is going to blow when it blows, and sun's going to shine when it shines. And so those do save us about 1/3 of our retail cost because we won't have to burn gas to generate that energy. But it does nothing to address our capacity costs, which is about 2/3 of one's retail bill. And down here in the lower right, growing versus declining load. Starting about 2009, we, many utilities, went from literally a century of seeing continuous load growth, give or take a war or a recession, but every year load was up 1% or 2% more. Every year you were looking at acquiring new assets, accessing new energy. And 2010, 2012, more efficient lighting, more efficient appliances, stable population, we now see declining load growth. So that limits us financially. It limits us to what projects we can take on. We have the generation fleet we need to meet the current demand. But if we saw growth in electric vehicles, which certainly we will, and more efficient heat pumps, which hopefully we will, that enables us to look at acquiring new generation capacity as well as sourcing new energy to meet our needs. And here is some, again, getting back to every hour of the day, every minute of the day, we must meet our load. Here we see these top lines, average Januaries and Decembers for HEA, and these bottom lines in the summer, Junes and Julys, throughout the day. And it's lowest at 3 and 4 in the morning. You know, none of us are up doing very much. The refinery's still running, and there's some heating systems going. But then we all get up and we make our coffee, we take a shower, we cook breakfast, we get to work, we turn the lights on, maybe we turn the equipment on at work. And then we get home in the evening and we cook dinner and we run a load of laundry, and then it tapers off again. And so there's a predictability to our load. It's a function of temperature. It's a little bit of function of whether it's a sunny day. There's far less predictability to wind and solar, and we know that. And when we discuss with an independent power producer about buying non-firm power from them, we have to factor in our integration costs. When the wind drops, we have to bring something else up immediately, a gas turbine, a battery, hydro, something, and that incurs some cost. One of the beauties of Tidal is, and I'm sure Levi will discuss this, but it is predictable 100 years in advance when that tide is going to flow. Another beauty of hydro is that unlike the wind, which sometimes is very sporadic, in a particular ebb cycle, the power out of a tidal generator will momentarily be zero and then smoothly ramp up and smoothly ramp down. And that's an addition of energy to our system that is easier for us to accommodate. It's completely possible to predict. And something probably most of you don't know is we have to request hour by hour when we take our natural gas a day before. We have to nominate when we take our gas. We have to coordinate with other utilities when we take our hydro. And so there are a lot of pieces that go into meeting this minute by minute demand of all of our members. And dispatchable power, although it's a big expensive dam or it's a fossil fuel with all of its downside, is the most flexible. Wind and solar are the least, and tidal is in between because of that predictability and because of the smooth nature of it. So I'll wrap up there and stop sharing and hand it off to Levi. I'll jump in the chat bar if someone has a question, but otherwise answer questions at the end. Thank you.
Thanks for that, Dave. And thanks everybody for being here today and being a part of this conversation. Thanks to REAP for inviting me to talk. I'm really excited to be here. I'm zooming in from Arapahoe lands in Colorado. I'm in Fort Collins at the moment, but my homeland is Denina lands. So I'm using I'm in my virtual space at the moment. This is home. This is Cook Inlet, or this is Ketchimack Bay, yeah. This first slide is it shows the This is also Denina lands or waters, I suppose. This is a photo I took looking to the west across Cook Inlet, standing up on the bluff at the East Foreland. And, in the distance there along the waterline, you can see the West Foreland. So that's sort of about 10 kilometers away, and Mount Redoubt is flying high. In the foreground here, you can see a tide rip just above my title here of the title block of the slide. So in this case, the currents were flowing.
Levi, you got to start sharing.
Oh, I got the same problem.
Hit share or hit that second share button, I think, and then it happens.
Okay.
Thanks, David.
And I did this. Okay. I'm trying to make you look good. All right. Thank you for that, David. So like I was saying, West Foreland there on the far side along the water line, Mount Redoubt. There's a tide rip here along the top of my tidal block. So the currents are flowing to the south, to the left, out the inlet. And one of the things that I like about this slide is that the oil platforms are visible as well. And to me, that's a reminder that if they could figure out how to get the gas out of the inlet, why can't we figure out how to get, and in all of the challenges that exist here in the inlet, including ice and sediment and everything else, I like to think that we can figure out how to do tidal energy. But before I dive into that tidal energy stuff, I just wanted to give a really high level plug, a really quick plug for some of the other things that are going on at NREL. So for everyone who doesn't know, the Cold Climate Housing Research Center joined NREL a little over a year ago. And this organization, I think these guys are great. They do amazing work on building science, and I think in particular incorporating Indigenous knowledge into their engineering and their technology, but also into their community outreach and engagement. And I think Indigenous knowledge is a core piece of who CCHRC is, and to me that's a huge addition to NREL, and something that I think wasn't probably as strongly incorporated into our mission as it is now. And so I'm really excited to have CCHRC on board, and to have for my employer NREL to have a home in Alaska, which is my former home as well, is also really exciting to me. Another thing that is that we're working on in sort of the marine energy and ocean energy space is we're working with BOEM to summarize the opportunities for wave and tidal and offshore wind resources around the state, and try to identify what some of the best options might be for, if in the future there was interest in developing projects on the outer continental shelf where BOEM has a jurisdiction, what those might be. And so this is a project I'm really excited about that we're getting started now. Another project that we're working on in the marine energy space is this pump storage hydropower project. Basically, as Dave was mentioning, you can think of Bradley Lake as a battery that you can sort of turn on or off whenever you want to, but you got to wait for the rivers to recharge it. But pump storage hydropower is where you actually can actively recharge a lake. You can pump water uphill to store that energy. And so we're evaluating different options for pump storage hydropower in Alaska. We're looking at along the rail belt in Southeast Alaska, and then also trying to identify some remote communities where this might be a good option. So those are just really quick 3 things I wanted to touch on. And now coming back to the marine energy picture, just to clarify, marine energy, when we talk about marine energy, we mean 5 different things: wave energy, tidal energy, ocean current energy, which we mostly think of as the Gulf Stream off the southeastern United States. Ocean thermal energy, harnessing electricity from thermal gradients in the ocean. Sometimes that's called OTEC. And then river current energy. One thing to note is that offshore wind is typically a separate, there's a whole separate group at NREL that works on offshore wind. We collaborate with them a lot and everything else, but it's not, in my world, it's not typically included in what we call marine energy. So if we're including offshore wind, we say ocean energy. But if we're not, we're talking about marine energy. The point of this slide is just that the US has a massive marine energy resource. And Alaska in particular has an outsized proportion of that energy. Almost half of our nation's marine energy resources are in Alaska. We've got 90% of the tidal energy resource and about half of the wave energy resource, along with some river energy resource. So, it's probably not, it doesn't come as a surprise to people who, especially people who live along the coast in Alaska, that it's a marine state, and our marine energy resources and our offshore wind resources are massive opportunities. Another thing that the Department of Energy's Water Power Office has been an initiative that they started a couple of years ago is what they're calling the Powering the Blue Economy. And there's a bunch of different areas here in this graphic showing different types of things that we look at in the blue economy, where marine energy might be able to help, contribute electrons, basically electricity, to support those industries. But the big takeaway that I have for this slide is the blue economy, all the work that goes on the ocean, including marine shipping and aquaculture and everything else, it's expected to double in size in the next 10 years, from $1.5 trillion to $3 trillion. And so the point there is just that this is a massive sector of the global economy, and it's expected to grow very rapidly. And if we can capture just a small slice of that, it could be a very impactful thing for the state of Alaska. And I guess I should say we are already a big piece of that with our fisheries, and we do a lot of work on the ocean, but the growth is expected to happen as well. Okay, next I just wanted to really quickly just highlight some of where the technology's at for tidal and river current energy. This is a photo of Ocean Renewable Power Company's RivGen device. This is in the community of Igiugig in Alaska. And this they've been running one of their RivGens in the community for a couple of years now. It's been really successful. They swapped a second device in. They're doing some retrofits on the old one. But to me, this project has been really successful, and the success grows from the leadership of the community and the collaboration of that community with ORPC. I think these two partners have just really been on the same page and working towards the same goal and working really hard to make this happen. And it's been a huge success, and I hope that success continues and they're able to do more of these types of projects around the state. This slide is a photo of another U.S. tidal energy company, Verdant Power. They deployed this tri-frame system in the East River about a year ago. That was also in a lot of ways a huge success. They generated 310 megawatt hours of power that they put into the New York City grid. And NREL actually was involved with them a little bit in terms of we were doing some materials research on these new blades here. You can see this turbine is being swapped in. They're basically demonstrating an operations and maintenance cycle for the turbine and showing how that'll all work. And as part of that, we collaborated with them and did some materials research on using thermoplastics, recyclable materials for these blades, which I think is going to be really important for the marine energy industry moving forward. Got a couple more slides on technology. These are from European companies. The Europeans have poured more money into tidal energy than we have here in the US. And so they've got bigger technologies. This is a 1.5 megawatt turbine. And this is another Orbital Marine Power is another Scottish company, and they have a 2 megawatt device, and they're showing promising results. But another thing that I'm just trying to clarify for everyone is that, you know, all these deployments are sort of one or two or a few devices. We're not yet, and so we're seeing a lot of success with that. But the next step, I think, is to start deploying larger numbers of devices and really scaling that up and working on the operations and maintenance cycles to be able to drive the costs down. And the question is, where is that type of work going to happen? And I think, as a former Alaskan and an Alaskan in my heart, that Cook Inlet would be a great place to demonstrate some of these technologies as they're starting to scale up. The resource in Cook Inlet is massive. It's over 30% of the nation's total resources right here in Cook Inlet. As David said, it's adjacent to transmission. There's space for multiple pilot projects. And I like this image here of the Agrium nitrogen urea fertilizer production facility there in Nikiski, because when we're talking about the future energy system and the future renewable energy sector, you know, e-fuels, which is basically where you make a fuel out of electricity. Maybe you pull carbon out of the air, you pull nitrogen out of the air, and you basically make a fuel from energy, and it's another form of energy storage. That's making e-fuels is seen as like a holy grail of making a renewable energy, reaching 100% renewable energy. And ammonia, which is one of the things that's produced in the process of making urea at this facility, is seen as one of those fuels of the future. It could be one of those fuels. And so to me, the idea that, you know, either you repurpose Agrium to produce urea or to produce ammonia, or you're using a renewable tidal energy as a energy source for the urea as a fertilizer, that seems like a really amazing opportunity where you could have like a renewable sort of a green fertilizer or a green fuel export economy from the state using some existing infrastructure that we have already. So now I'm going to dive into the measurements work that we did here in Cook Inlet, right off of the East Foreland. So that big purple arrow points at the East Foreland. So I'm going to zoom into that site. This graph up on the upper left shows basically the East and the West Foreland. And we focused most of our work this summer right off of the East Foreland. In the lower right, this orange torpedo looking thing is our stable moor mid-water mooring system. And it has these acoustic Doppler current profilers on board. These things are amazing instruments. I could nerd out about them for hours, but basically they measure the velocity continuously in the water column, both above and below these buoys that are flying in the water column. So that's what these sort of beams are meant to indicate, is those measurements. We also use this bottom lander platform shown in this photo in the middle of the channel. And then we also did transects back and forth across the channel with a downward looking one of these instruments where we measured the velocity. So most of the data I'm going to be showing now is velocity data that was measured this summer. So I'm going to spend just a minute on this slide. So the upper left-hand graph is a map of that spot right next to the East Foreland. The blue coloring is showing the water depth. So you can see there's this channel that's about 55 meters deep. And it's about a kilometer offshore is the middle of this channel, a little more than a kilometer. The red arrows are indicating the direction and magnitude of the flow. So these arrows over on the right here are just for scale. So we're talking about 1, 2, and 3 meters per second. This is the depth average velocity. And then these little icons indicate where those 3 moorings are that I'll talk about that data in a minute. This shows where we are in the tidal cycle when we made this transect. And then this lower panel shows actually the data from the transect. And so these reds are indicating the flooding current heading up towards Anchorage, flooding in the inlet. And what we see is we see really strong currents at this site. At the surface, especially right near the foreland, there's currents over 3 meters per second. And this is right about during peak flood. As we step forward in time, the flooding currents start to weaken a little bit as you approach high tide. And as you continue to step forward, then you're getting into the slack. So the slack actually occurs a little bit after high tide at this site, and the currents start to reverse. And you see now the blue is indicating that it's coming out of the page towards you. But again, you're seeing very strong currents throughout this channel. It's a really impressive resource. This Q is the total volume flux at the site. And so we use that to calculate sort of theoretically how much power you could make at this site. And just in this little section of Cook Inlet, there's a potential for like 100 megawatts or so based on these volume flux calculations. So just stepping forward, again, now the ebb is starting to weaken. You get back into the low slack, and then the flood starts to happen again, and the cycle repeats itself. So that's our transect data that we got. This is all just like super high quality data. I'm really proud of this. I should have said the photo over there is showing the ADCP mounted on the pole that we had in the water to make these measurements. Okay, now just quickly our bottomlander data. So this is now a time series from a point in the center of that channel. And you can see this is over 2 months. And what the middle row is showing is, again, the velocities. And so the reds are the floods heading up the inlet, and then the blue is when it reverses and heads back out, ebbs. And again, we're seeing like just continuously, like clockwork, these really strong 3 meter per second currents. The bottom panel is a measure of the turbulence, so how much the currents are going like this in the water column. And that's really important. That was a big piece of what we were measuring here, was to measure the turbulence, because knowing how turbulent it is really important for designing technologies that can survive this environment. Because what they learned in the early days of the wind industry is that turbulence rattled the wind turbines and caused them to break and fail. And so designing devices robust enough to handle the turbulent conditions is really important. And so knowing, first of all, what those turbulent conditions is extremely important. And that's what this data is, and that's what this tells us. So that perspective was sort of like difficult to take it all in. This is just like a zoom in on just a 4-day period within there. So here you can see a little more clearly the reversing currents and how that's phased with the tidal cycle. And so I just thought it'd be interesting for people to be able to see this up a little more closely. But the point is this is just like a totally amazing data set. We got really high data recovery here. And so last slide on the data, here I'm plotting the current speeds at for different velocities. So the darker red lines are for the stronger currents, the floods. The blue lines are for the ebbs. And again, this is just showing you really do have like over 3 meters per second peak floods from about 50 meters up towards the surface. And our instruments, they don't measure, they have issues, reflections from the surface. And so we don't get data all the way to the surface in these cases, but you can pretty safely assume that these lines go basically straight up, or you can kind of extrapolate to the surface what those lines should be. And then this plot here is for the tidal energy technology developers in the audience. We're seeing the average, tidally average power density is it's as high as like 5 kilowatts per square meter. here at about 20 meters. And then on the peak floods, you've got 24 kilowatts per square meter, and ebbs are over 15 kilowatts per square meter. So again, just a really energetic resource at this site. So again, kind of coming that on the data and coming back to where the technology's at. This is a plot of the cost of wind energy since 1982 through 2012. So 30 years of a lot of federal and state investment in making these technologies, bringing wind energy technology to where it is today. And the point here is it's going to take time for us to prove that these tidal technologies can work, can survive for 10 years, right? Like, you don't know that a device will work in the ocean for 10 years until you've had it in the ocean for 10 years. But I think it's worth it because we see what's happening in wind today in terms of, gigawatt scale wind farms, both on land, and now we're seeing offshore wind farms of that scale. And I think in the future, we're gonna, our demand for energy and electricity is not gonna go away. And I think having tidal energy as another option, here in the US, in Alaska, in Cook Inlet is useful, but also globally. And so Alaska, I think, has an opportunity to play a role at this early stage. And maybe in the future, we can show other countries and other parts of the world how to do this right. And this is just really quick, I think, technology developers, they're really the leaders in this space. They're doing a great job. They do so much of the hard work of designing technologies, getting them in the water, testing them. And I think the national labs and universities, we can play a critical role in supporting the technology development, supporting industry. And this is just kind of a little plug for some of the types of things we're doing. My colleague Robin Murray here, she's really into composite materials. She's working on a wind turbine blade in this case, but she's especially passionate about tidal energy. We do testing of those blades, where structural testing. In the lower left here, we're testing a generator. Of course, labs also do a lot of numerical simulations work on designing arrays. And we also do this work. This is a verdant blade where we instrumented it to measure the loads on the blade. So this is all work that I think labs are really excited about doing, and we want to work with industry partners to continue to do it. And I definitely think there's a role for universities to contribute to this as well. The other big thing that we think a lot about, and especially at PNNL, is a leader, Pacific Northwest National Lab, based in Washington State. They are a big leader in looking at the environmental impacts of marine energy technologies. And one of the big ones that people are concerned about, obviously, is collision risk. And I think this is something, the Iggy project has collected a lot of data about fish collisions, and there have been just, I think, 0 fish strikes in that project. But I think we need to continue monitoring this. I know beluga whales are a big concern in Cook Inlet. And so I want to make sure that we're collecting data on this and not and continuing to think about these environmental risks, basically. And PNNL is really leading the way in that. And University of Alaska Fairbanks actually is really involved with Iggy as well, I should say. So definitely need more of this kind of work. So in conclusion, Cook Inlet is this massive resource. The technology is at a stage where we need to start doing these pilot projects and really demonstrating that the technologies can work for long periods of time. And I think there's this blue economy opportunity. The growth in the blue economy is going to be massive. And so this question is really to you guys, to the state of Alaska, the public. What do you want Alaska's role to be? To me, I think it starts with a conversation about how do we do tidal energy in Cook Inlet? ORPC has the preliminary FERC permit to develop technologies at the East Foreland. They got that over this summer. But there's also Turnagain Arm, Tidal Power Corporation. They're looking up closer to Anchorage at this hot spot in particular, you can see in the map here. But there's other sites for other technologies. And so I think all of us working together in terms of thinking about what the research questions are, what are the concerns, how do we do this right? I think having that conversation is really where this starts. So that's all from me, and hopefully we still have some time for questions. Thanks, everybody. And thanks to all the project partners who helped make these resource measurements happen this summer. Couldn't have done it without literally everybody here. Pacific Northwest National Lab is involved in this project as a whole. They provided a lot of the modeling support. Sandia National Labs is going to help with some of the data analysis from this project. And then these other partners were directly involved in the measurements this summer. So thanks a ton to them.
Cool. Thank you so much, David and Levi. And it looks like we have a bunch of questions in the Q&A here. So maybe, yeah, if you all want to, I know David has answered a few already just through typing. But yeah, with our final 12 minutes here, if you all want to pick some that stand out to you and do our best at answering those.
I see this question from John Brelby about the major impediments to tidal power were silt, sinker logs, winter ice, and dangers to marine mammals and salmon. I think, so we did collect some data on the silt. We're still kind of working through that. I didn't have that ready for this presentation because we just got that data back, not too long ago. But I think we'll have a lot more knowledge on that soon. And then that data will be made available kind of to the technology developers, and hopefully that will help them design bearings and seals for this. As far as like logs and ice, I think those are I think logs are a challenge that we can deal with. And ice that's going to be a big one, but I mean, the oil platforms figured it out. I'd like to think that we can do it as well. And yeah, the environmental concerns, I think I spoke to those a little bit. We need to continue with that work. Just scrolling through here. Sydney, I don't know if you've identified particular questions.
Yeah.
Go ahead.
Let's see. And also just FYI, you're still sharing your screen. But I think I don't know. There's a lot of good ones here. Bob Shavelson asked if you could talk more about the collaboration with BOEM and Cook Inlet.
Yeah, I can go back to that slide. I guess I have to share my screen again. But it's really, my colleague Elise can speak to it better, but it's really about identifying other sites for other technologies. For example, offshore wind. I think offshore wind is going to be a big focus of that. But we're also looking at tidal energy and wave energy resources. I think offshore wind is going to be a focus because it's basically a technology that's here much sooner, and I think BOEM sort of does have that perspective of like, okay, who are we going to be giving permits to? And so I think we're just trying to help them identify what regions might have good resources and what kind of some of the competing use issues might be with developing those projects. but BOEM's interest, we are going to be including Cook Inlet because I think it's important to provide that as a context, but BOEM is mostly interested in like the outer continental shelf. So that's federal waters below the 3 nautical or beyond the 3 nautical mile boundary where state waters extend. Yeah.
Great. And then we have one sort of related to what you were just saying from Ryan. This one is for David. So Cook Inlet is well known for its tidal resources, but has HEA considered harnessing wave energy in the lower Cook Inlet or north of Kodiak?
HEA has not. Wave energy is a lower energy resource than tidal currents. Also, tidal current, although it has great potential, is beyond our planning horizon. You cannot get utility grade equipment at a utility scale. Wind, solar, and gas, you can get 20 and 30-year lifetime units. Therefore, you can get a 30-year loan on it. Therefore, you can finance it. And tidal is not at that point. So we're very supportive and very hopeful about it, but it would not help us meet our 2025 goal or a 2030 goal because it's just not that far along yet.
Yeah, and
despite its great potential.
Yeah, and I totally agree with what David's saying. I think my point about you don't know it lasts 10 years until you tested it for at least 10 years. Was meant to speak to that, and financing organizations, they're not going to back a loan for a device that they don't have confidence in, and the way that we demonstrate confidence in them is through those testing programs and through repeated, connecting all the dots on the paperwork of this is what the operations and maintenance costs are, these are what the capital costs are. This is how the whole project pencils out. We know the device is going to last for 20 years because we've had 50 or 100 of these things already last that long, and so that's going to take time. But I would like to think that Cook Inlet and its harsh environment would be a great place to demonstrate these kinds of technologies, because you can say, hey, this thing lasted for 20 years in Cook Inlet. I think it'll have an easier time surviving other places, and so hopefully the banks would support you.
And we're somewhat unique in this convergence of road and grid and high tidal currents. Plus, we are in an area with high energy costs, so better to displace 24-cent retail power than a national average of 13 cents. So many factors in our favor, but to meet our renewable goal, we are looking to storage hydro and wind and solar, and are trying to support tidal in the ways that we can.
So I wanted to hit this question about the wave energy really quick. So just so people know, tidal energy technologies are sort of, even though they're still 5 or 10 years away from being commercial ready, wave energy technologies are even earlier, right? We're still trying to figure out what a wave energy converter looks like, and there's a lot of research in wave energy technologies going on at NREL. I just haven't talked about that today because I think because it's so much farther out, and also because Alaska's wave energy resources are farther offshore, or they're along the Aleutian chain, they're not kind of right next to the population centers like Cook Inlet is. To me, the sort of near-term opportunity for marine energy in Alaska is tidal energy in Cook Inlet.
And I know Mark Misteller in the chat was flagging his question on turbulence. And there's actually a couple of good questions on turbulence in there, if you can see them, from both Mark Misteller and Mike.
Can you read one of them off? I'm having trouble finding it.
So Mark's is regarding turbulence, do you have a sense of whether East Forelands turbulence is low, medium, high relative to what the technology can handle?
I haven't had a chance to complete that piece of the analysis yet. I apologize. I mean, I think it's, from what I can see in the plots, my guess is that, near the bottom, the turbulence is going to be very intense and the currents are weaker down there, right? Like, but this is the case at all tidal energy sites. And so as you go farther up in the water column, the turbulence decreases and the currents increase. So that's like some of the advantages of being higher in the water column. Disadvantages of being higher in the water column include things like ice and vessel traffic and so on. And so finding that sweet spot in the water column, I think, will be something for the technology developers to figure out. But we're providing the data that will inform those decisions.
Great. And Kenneth had a question. Are there other remote villages looking into tidal energy besides Ugiagik?
Yeah, we've done some work with False Pass, Alaska. They've been really interested in tidal energy. I've talked to communities, Seldovia, Cake, Alaska. So it's something that comes up, but I think the thing I always try to be really clear with people about is when they ask me this is like, yes, I want to help you. But just so you know, the technology's 5 to 10 years away, and I think ORPC has made some massive advancements in the last few years, and I think they're ready to start doing more projects where they show that their technology can be successful in those environments. But whether they're bankable yet, I think is another, you'd have to talk to them about that. But yeah. It's certainly something that people around the state and around the world are interested in more and more. Yeah, and I see Shelley's question about how do we move the research forward? When will these alternative energy resources be ready? Like I said, it's the tidal and wave energy, that's not really relevant for Cook Inlet, but tidal energy is still several years away. But wind and solar are here now. And I think HEA is doing a great job in terms of getting this battery in place so that they can integrate more renewables. Those are the types of things that we can do now. And as far as this research, I think having that conversation and talking about what Alaska's role is going to be in these pilot projects to demonstrate the bankability of technologies, to me, that's the next big step that we need to take.